Okay, so just a reminder what an addition reaction is. So in addition reaction, we have some sort of unsaturated hydrocarbon. Unsaturated hydrocarbon. We have to break the double or triple bond in there, and then we're going to add new atoms in wherever we broke that double or triple bond. So, like if I'm looking at this example here, what's happening is I'm breaking apart this bond. I'm breaking apart this bond, so that's gone. So now I have the capability of adding in a bond right there. And I kind of have a bonding electron that's ready to be bonded in, and so what happens is the hydrogen that's in excess is going to add to those two spaces. And so we always have that breaking apart. We get an unsaturated molecule becoming a saturated molecule in a addition reaction. If you're strictly adding in hydrogen, that's called a hydrogenation reaction. I just wanted to go through a question here, and then we'll look at substitution. So propene reacts with excess hydrogen. Do you guys want to try this, or should I just keep talking? Keep going? Okay. So propene, we'd have to remember prop is tells me I have how many carbons? 3 carbons, so 1, 2, 3 carbons. Now it doesn't tell me where the double bond is, so what does that mean? It doesn't matter, right? If I'm going to start counting, it doesn't matter, so this would be my propene molecule. Remember when you're bonding anything to carbon, whatever it may be, that you're not violating the octet rule. Quite a few people did that on their quiz where they violated that octet rule. So I'm going to react this with excess hydrogen. And so what's going to be formed here then is, assuming I'm underneath the right conditions, I have a catalyst or sufficient temperature and pressure, I would break apart this double bond. So this double bond is going to break apart, and now I have the capacity to form a bond here and a bond here. And the hydrogens would come into those places. So this would become a propane molecule, and that's where the new ones would be added in. One more here. So butene reacts with excess bromine. You have to be able to look at like a reaction and be able to identify, okay, that's a addition reaction. This is an addition reaction because I have something that has a double bond in it, and it's reacting with a halogen or hydrogen. Usually, that indicates we have a addition reaction. So butene, so but1 would mean there's a double bond on the first carbon. 2, 3, 4, and my hydrogens would look like this with excess bromine. So Br. And so same thing that would happen here is I can, again, underneath the right conditions, this double bond is going to break apart, and now I can add a bromine on this molecule and on this molecule. So the bromine would add in there and there. So when I'm writing this out, my molecule would look like this. The molecules on the end are staying the same. These now become saturated with these bromines being added in. And so also to kind of extend on what we looked at yesterday, what would I name this molecule? I just say dibromo. Right, I'd have to tell what number it was on, so this would be a 1,2 dibromo butane. So that's addition reactions. Everybody kind of feel a little bit more familiar with that than yesterday? Okay. We're going to look at substitution reactions. If you're following along your notes, just grab those out. So a substitution reaction is the breaking of a carbon to hydrogen bond in an alkane or in an aromatic ring. Remember, an aromatic ring is breaking the bonds within this benzene. And because there's hydrogens out here, we're going to be breaking one of these bonds on the benzene ring. So substitution reactions are the breaking of the carbon to hydrogen bond in either an alkane or an aromatic ring, and then we replace that with another atom of another group. It could be a hydroxide, it could be a halogen. There's a lot of different substitution reactions that you can add different molecules in for that place. These reactions would only occur slowly at room temperature, so they're not like a very fast, naturally occurring reaction. And usually for these reactions to happen, you have some sort of electromagnetic radiation as a catalyst. So sometimes you need certain types of light will increase this reaction rate. Let's write that down before, right? We'll look at this reaction here. So here I have propane is reacting with bromine, and so if I ignore what's happening to ignore this for right now, and just look at my reactant side. So I have propane and bromine reacting in the presence of light. What's going to happen is one of these hydrogens, it doesn't necessarily matter which one, is going to be substituted out for a bromine molecule. And so because it doesn't matter if they don't specify where it's going to switch out, that's why we can have multiple isomers, I guess, or multiple isomers being formed, right? I could have a 1-bromopropane, I could have a 2-bromopropane, I could have a 3, or like a 1,2, I guess is the only one that I could make. The other thing that's going to happen here is the hydrogen and the bromine are going to switch places. Alright, so let's look at exactly how to do that. Benzene rings are pretty stable, but they will react slowly with halogens, that carbon to hydrogen bond. Okay. So full replacement can occur in the benzene ring. All hydrogen atoms can be replaced by halogens if you have an excess amount of halogens. So essentially what they're saying is that remember, benzene looks like this. Really, there's these hydrogens on there, because the formula for benzene, anybody remember what that is? C6H6. So really, actually, every single one of these hydrogens on the outside could be replaced by a halogen, assuming that you, again, have enough quantities and the right conditions. The bonds within the benzene are a little bit harder to break, those alternating double bonds. It's a pretty slow reaction, so it says here it requires light as a catalyst, and sometimes other ions as well. Okay. So let's look at a reaction. So benzene reacts with chlorine in a substitution reaction. Literally the example that's on the other page. So let's go with chlorine. And so you have to be able to draw out the reaction. So benzene looks like this. It's reacting with chlorine, so this is benzene. Reacting with chlorine. Remember, chlorine is diatomic when it's by itself. That's with chlorine. Oh my goodness. That's definitely not how I spell chlorine, but we're good. Okay, and what happens here is I'm just going to have a swapping, right? So that's why it's called substitution, is I'm really just substituting one of these hydrogens for one of the chlorine. These guys substitute, or they're switching places. And it doesn't matter where on the benzene ring I say that chlorine bonded onto, it would still be a 1, or it would still be a chlorobenzene, regardless of where I put it, because there's only one of them. Yeah, unless they say there's a ton of excess, you're just assuming that you switch out one. Because realistically, you could switch out every hydrogen with it, but you usually just assume one unless they say there's multiple. What else would be being formed? HCl, right? So the hydrogen that was here is switching places with the chlorine. So I also would have HCl, so hydrogen chloride being produced. Question? Yep. Yep. If it wasn't excess, you could have multiple molecules, so then I could have another molecule that said, okay, now I have a chlorine and a chlorine. And then I could essentially keep adding on chlorine molecules, but you don't really ever see that. You'll just see more or less what type of reaction is this, or what would be produced, assuming that it's not in excess usually. They'll say, okay, there's 2 molecules, or there's 1 molecule of this. Any other questions? Oh, I apparently have one back here. Propane reacts with fluorine. So propane looks like this. These are all hydrogens. Reacts with fluorine. So remember, fluorine is diatomic when it's by itself. So what would be produced? Anybody know what would be produced? Substitution reaction. So hydrogen fluoride, so yeah, one of these hydrogens is switching the places with this, so hydrogen fluoride. And I could create multiple molecules, right? I could have this fluorine going on this molecule, or it could go on this one, or it could go on this one, right? It has multiple options for the bonding. What I'm looking for is that you give me at least one that is correct. So as long as you are creating a molecule that looks, and you have a fluorine on one of them, the rest of it is fine. So this would be a 1,4-O propane. I could also create a 2,4-O propane if I wanted to. Why couldn't I have a 3,4-O propane? Right, I just would end up numbering from the other side. Let's see. So CFCs are used as refrigerators to create bubbles in plastics. CFCs. Okay, so it says that we're producing. So it says draw the structural equation for carbon tetrafluoride being produced from methane reacting with chlorine. So here's methane, and I think this is the one in your notes. Methane is reacting with fluorine, so fluorine. And they tell me that I'm producing a C, like a CFC, which is, in this case, it's a C, where my carbon tetrachloride is the first thing that's going to be produced. What the heck am I doing? Oh, okay. Don't mind me. There we go. I figured out this one. So the first step in creating a CFC is to take all those hydrogens out and replace them with chlorines. So I have my chlorine that's diatomic. And all of these then become chlorine molecules. All of them. Pardon me? Yeah, I just ignored that part of it. I'm just looking at this part. Well, they tell me what it makes. They tell me that carbon tetrachloride is produced from reacting methane with chlorine. So I know what's being produced. My question is, though, what or how many chlorines do I need here? Why 4 and not 2? Because it's tetra, right? And we have a swapping. We don't have a total break apart that chlorine molecule, just use that chlorine. So really, each of these is going to switch. So we need 4 of these, and I would be producing 4 hydrogen chlorides. And so now you're just going to go finish up with 6 that asks you about addition and substitution reactions. It should be pretty easy to tell automatically what's addition, what's substitution. Addition reactions start with an unsaturated hydrocarbon, so propane or like an alkene or an alkyne. Substitution, you have saturated molecules reacting with some sort of usually halogen, and they would switch places. In the answer booklets, I've put down multiple molecules that could be produced. As long as you're giving me one of those molecules, you can consider your answer correct. Okay? So, just as a reminder for the people watching the video, let's just go erase all that side. Just a second. We're doing homework 5 and homework 6. Homework 6, you said all of it. Homework 5, I said no.
6, 7, AC.
6, 7, AC, and then 8 to 11. Okay, so first of all, if you actually watch this video, you're going to come see me on Tuesday morning, and you're going to say snuffleupagus to me. And if you don't, I know you didn't watch this video. Cheaters. And if you heard this, don't tell the other people. What? So, we're looking at alcohols and elimination reactions. So alcohols have a bunch of consumer, commercial, and industrial processes. Alcohols contain one or more hydroxyl groups attached to the hydrocarbon. And so we have like kind of like a OH side chain. As soon as you add an OH side chain, what would that do to the intermolecular forces? Change it. So let's say if I started off with this, and I change this now to a propanol, so I add a hydroxide here. So they both would have London dispersal forces, but this one here would that have dipole-dipole forces? Yeah, this is causing it to be polar. So it would have dipole-dipole forces. Would it have hydrogen bonding? Yes. Yeah, because I have the hydrogen bonded to the oxygen in there. And so, in terms of the boiling point, what does adding a hydroxyl group do? So it'll increase the boiling point. What about solubility then? Makes it soluble as well. Okay. So here's some characteristics explained by the hydroxyl group. They have a relatively higher solubility in water than other hydrocarbons. That is because they are polar, and polar molecules will dissolve in water. They generally have cleaner burning properties. They would boil at much higher temperatures, so higher boiling point, and they're much less volatile. So they're say like ethanol is more stable than F8, for example. I'm going to ignore the comment. So here we go. So short chain alcohols are much more soluble in water than longer chain alcohols. So for example, ethanol is more soluble in water than non-enol. Right? Yeah. Right, and that would just be because of the size, the polarity, and the hydrogen bonding. So the same kind of thing as I said before. This one right here, right? If I had like 7 or 8 or 9 hydrocarbons and then just a hydroxyl group at one end, this end is going to be non-polar or polar, sorry. And this end would still kind of have polar properties, non-polar properties. That wouldn't want to mix as well in water as this end would. So as the carbon-to-carbon chain increases in size, so does the solubility of alcohols in non-polar solvents. So if I have like that non-enol, assuming that's a thing, that would be more dissolvable in oil than opposed to ethanol, because it's more non-polar than this polar. And so just kind of like a little bit of bio in there, right? Hydrophobic, the hydroxyl end would be, hydrophilic would be because it would be polar, so it would mix in water. The rest of the carbon chain is still essentially hydrophobic. It's just carbon and hydrogen. It has no dipole-dipole forces, so it wouldn't really mix very well in water. If you have more than one hydroxyl group, that would increase my solubility. That if I increase my solubility, that's also going to increase my boiling point. So the more hydroxyls I add, the more the solubility increases. And the same thing with boiling point. Boiling point increases with the chain length and the number of hydroxides. Pretty good? You weren't good? Yeah, you're good. So classify. Production of methanol, I'm not too worried about methanol and ethanol production. Ethanol is produced by the fermentation of sugar or starches. Yep, that's how you make it. Alcohol. The consumable type. So just a few consumer uses here for ethanol and methanol. So methanol is a solvent in many paints and varnishes. It's used as race car fuel and is highly toxic because we have this intermediate phase of it being formaldehyde. So sometimes like methanol will dehydrate, so undergo dehydrogenase, so it's a formaldehyde. So that's why methanol can be intoxicated, because it can be formaldehyde. Same thing with formic acid. causes metabolic acidosis and tissue injury. Ethanol is the one that is consumable. Anything with a alcohol concentration of 50% is consumable. And there's kind of the reasoning of what happens to alcohol when it goes in your body. Breaks down into acetaldehyde, gives you a hangover, and again into acetate, which is what you smell if you smell alcohol. Regardless, this biological process is still happening. Maybe just at a faster rate. Maybe their body metabolizes alcohol faster. Okay, so simple alcohol names, right? So what I do to name a alcohol is I take the E ending and it goes to a all ending. So that would be methanol. Same thing, methane. I take out one of these hydrogens and put a hydroxide in, and that becomes ethanol. It wouldn't matter because there's only 2 carbons, right? Okay, steps for naming alcohols to go through. Pretty much the steps are the exact same for naming alkanes, alkenes, alkynes, halogens, or hydrocarbon derivatives. The first thing you need to do, and which again, if you messed up on the quiz, which is find the longest parent chain. Because we're now looking at alcohols, we want to include the alcohol functional group as part of the parent chain. There is, like, once you move past 1020, there is when you have longer chains that the alcohol is not part of the parent chain. You name it as a side chain, as a hydroxyl, but that's not what we look at it as. We always try and include the hydroxyl group as part of the parent chain. So you change that ANE, add a AN prefix to the carbon to carbon. I don't know what that means. So really, add that O-all ending. So change the ANE ending. So it goes from an ANE ending to an O-all ending. And the side chain naming would be the same. So whether it's an alkyl side group or it's a halogen side group, you're going to name them the same. So methyl, 3-ethyl, 2,4-dichloro, whatever it is, your naming of the side chains are going to be the same. So looking at naming this guy right here, here is my parent chain. Why not? It doesn't include the OH. It does include the OH. If the OH was here, then that would not include the OH. Right, but it's bonded to that. When I look at it, it has to be bonded to the parent chain. It has to be part of that parent chain, because I can't keep this as part of a chain, right? That doesn't work that way. Not included in the parent chain. Well, yeah, it's a side branch of the parent chain. Yeah. It could not be included in there because OH now, right? This is satisfied in terms of oxygen has enough, and it's bonded to this hydrogen, so it's satisfied. It couldn't keep branching on like a carbon does. All right, so let's name this. So here's my parent chain. This hangs off the parent chain, so that is okay. So this is what type of a alcohol? How many carbon, or how many? Pentanol. So right, this is a 1, 2, 3, 4, 5. If I was going to name this, so it's a pent to all. The same way that I need to number where the double bond is occurring, if it's an alkene or an alkyne, I need to tell where that hydroxyl group is bonded a part of. It would be a 2-methyl pent to all. Yeah. Yeah, it's just like I was probably like slipping pictures together and it just cut. Yeah. Okay. Do I need to? I don't think we talked about that, so I'm going to skip. All right, so let's just look at. Oh, did you need that? Sorry. Okay. Okay, so I haven't seen like a old diploma question or anything that deals with this, so it's kind of, we'll just skim through it. So primary alcohols are where a carbon carrying the hydroxyl group is bonded to one other carbon. Right? And so this is on the end. So the only time you can be bonded to one other carbon is if it's on the end. And so that's a primary alcohol. A secondary alcohol is if it is bonded to two other carbons. So right here, this group with the alcohol in it is bonded to a carbon on the outside, so a secondary carbon, or a secondary alcohol. The third type is a tertiary alcohol, which means that that group with the hydroxyl on it is bonded to three other carbons, right? And so this carbon is bonded to three other carbons. Those could be this methyl group, so they could be entire side chains. It's more of just a naming, the type of the secondary, tertiary, primary alcohol. We don't really focus on that too much. We just focus on that IU pass name. Yeah. Right? This is attached to a carbon, this is attached to a carbon, this is attached to a carbon. Instead of this one, it's a carbon here, and then a hydrogen. Okay? Alright, so alcohols that contain more than one hydroxyl group are called polyalcohols. So their names indicate the number and position of hydroxyl groups. So, for example, if I'm looking at this, there's a carbon 1, 2, 3, 4. So it's bute, right? It's a bute. And then I need to say the name, like the number of both of those. So I would say, yeah, I would count from here. So 1, 2, 3, 4. So this is a butane. You'll see it written both ways. I'm going to show you both of them. So butane, and this is a 1,3-diol. Diol, right? So di because there are two, all because it's a hydroxyl. You may also see it written like this: butane 1,3-diol. Sometimes they take the E out, sometimes they don't. It kind of depends on what you're looking at. Sometimes they keep the A, and sometimes they don't. You'll see it written both ways. Pardon me? Oh, no, right? Yeah, so when you're naming these, make sure you're paying attention. Is it a hydroxide or is it a methyl side group? Or like, it's sometimes when the letters are close together, you might get them mixed up. So make sure you're paying attention to that. The next one, so we can also add in hydroxyl groups to cycloalkanes, cycloalkenes, or benzenes. And so what would you name this guy right here? Cyclopentane. So cyclopentane, and then what? 1,2-diol, right? A 1,2-diol. It would be a 1,2 because we just want to put those numbers on the lowest number of carbons when we're counting, so 1, 2. Di because there are two of those hydroxyl groups. Everybody's okay? So far, so good? So you want to take a second, name these, and draw these. Okay, so if I'm naming this guy right here, you have to start with the parent chain, so find that longest string of carbons that includes the hydroxyl group bonded to one of those carbons. So I can start here, and then there's a carbon here, so that's a 1, 2, 3, 4 carbons. That's my main carbon chain. There is not a carbon attached to there. That's just saying that there is a hydroxyl group attached to that one carbon. So if I was going to name just the parent chain there, I'm going to start numbering by the hydroxyl group. So 1, 2, 3, 4. So that would be a bute and 1-ol. And I also need to include that other side chain. So that's a 3-methyl butane 1-ol. Is that your time to work on the next one, Zach? Okay. Live. Okay. So this one, there's only 2 carbons in that center chain, so it's a monkey's eat, so it's a F. So it's a F, and then because it's on 2 different carbons, you have to tell me the location, so 1, 2, diol. Next one, you have to draw it, obviously, so butane 2-ol, so I'd have a 1, 2, 3, 4 carbon structure. On the second one, there is a hydroxyl group, and the rest of these would just be hydrogens. And make sure that when you draw your hydrogens, you're including your octet rule. Just for future reference on a quiz or a test or review, whatever it is. If you do not put your hydrogens there, at least by showing a dashed line, I'm going to mark it as you don't know where they go, because a lot of people were getting things wrong and violating the octet rule, so I need to see that you know where the hydrogens would go. Yeah. And so the next one, propane 1, 2, 3 triol. So your structure that you drew should look something like this. So 3 carbons. And then the oxygens, if you wanted to bond them all on one side or you alternated them, it doesn't matter as long as they are on the 3 different carbons. Okay, naming alcohols, we're okay? Okay. I probably would have just saved this lesson for tomorrow, but I just want to just get this video finished, so I'm just going to move on. You guys will get tomorrow to do the homework. Okay, so elimination reactions. What time do we have enough time? 10 minutes, okay. So the last thing we're going to look at here today is another type of reaction, which is elimination reaction. So elimination reaction, and we're going to look at two types of ways we can produce ethene. So the first one is the cracking of ethene. Usually cracking has to occur under high temperature and pressure. And essentially what's happening is I eliminate a set of hydrogen molecules from the alkane. So in this structure, what's happening here, a whole bunch of high pressure and temperature. And these 2 hydrogens are going to be removed, and I can then form a double bond in the middle. So elimination reactions are when we're eliminating something from the side chains, and we're creating a double or triple bond. That's what elimination reactions are. Eliminations are the opposite of addition. So the what was it? Oh no, yeah, exactly. So the other way would just be an elimination reaction. A lot of the time we can also produce ethene by a dehydration reaction, which is a type of elimination reaction. Dehydration means you're probably removing what? Water, right? And so I can produce ethene from ethanol because I would take and remove a hydrogen and a hydroxide to produce water, and then I'm left with the capability for carbon to form another set of bonds, and they form a double bond. All right, so let's look at an example. We can also eliminate a halide ion, which is a halogen. So here's an example. Write a structural formula equation for the preparation of butene from 2-chlorobutane in the presence of a strong base. So there's kind of a lot of things you have to look at in this question. Preparation means, if I'm preparing butene, is butene a product or a reactant? If I prepare butene, is it a product or a reactant? It's a product, right? So butene looks like this. On the second carbon, there would be a double bond. And so that's butene. Oh, sorry. What's wrong there? What's wrong with what I drew? This one violates the octet rule, right? So this would be butene from 2-chlorobutane. So 2-chlorobutane would look like this. So 1, 2, 3, 4 carbon chain. On the second one, there is a chlorine, and everywhere else, there's hydrogen. Oops, there's one on the end here, hydrogen. Sorry, and I'm just going to draw these in for the sake of my example here. There's a hydrogen back there and a hydrogen here. Those are some real bad H's, but H's nonetheless. Okay. So I have chlorobutane, and then it says in the presence of a strong base. What do you think that means? It's telling you that it tells me what it's reacting with, but what would it be reacting with? Pardon me? OH, right, yeah. So we're actually reacting with a OH negative. So this is one of the more complicated elimination reactions. It's almost a reaction in itself that you kind of need to memorize with a strong base, because we're going to see something that is a little weird. And so, compared to what we think would happen. So this is actually a type of dehydration reaction, which means that I'm going to form what? Water. And so what's going to happen is this hydroxide ion is going to combine with one of the hydrogens. And I know that I'm going to... Why am I choosing this location right here to remove it from? Pardon me? Let's put your note. Because that's where my double bond ends up being, is in the middle. So I have to remove a hydrogen from one of these in the middle. I also end up removing what? That Cl. So what's going to be produced is a water from this right here being removed, and just a chlorine ion. They switch places. The hydroxide ion and the chlorine ion will switch places. The chlorine came from this guy right here, because remember what I needed to do is create a double bond. I needed to create a double bond right here. So I got rid of this hydrogen by adding it to the water, but then this guy was just hanging out, so he comes into the solution. Again, kind of a very unique one. That only occurs when you have a strong base. A strong base means hydroxide, yeah. Okay, one more quick question, and then we're done. The elimination of elements of a water molecule from an alcohol is the second most common method for preparing an alkene in the lab. Write the structural formula for the preparation of butene from butanol in the presence of a catalyst. So I'm preparing, I'm preparing butene from butanol. Butol, right? So there's a hydroxide, all of the rest of these are hydrogens. Anybody have an idea of what would happen here? I'm gonna undergo dehydration, right? So these two here are gonna come off as a water. So add water, and that would be it. Yep. I don't need to add anything. I don't have any sort of anything else being added here because I'm not producing anything else. I just need to create a double bond in this location that it told me. Sorry, what's that? Where did I get my second H from? When I dehydrate this, sorry. These are all hydrogens, right? So, if I have the catalyst, what's going to happen here is that's going to prompt the hydrogen and the hydroxide to be removed in the form of water. And now these guys are left wanting to, now I have two lone pairs here. And so they would come together and form a double bond right in the middle. Alright, so that means if you are not here, you are doing homework. What number homework is that, 7 then? Homework 7 as well. All of that. Homework 5, 6, and 7 will be due to be checked on Tuesday. Make sure you're checking your answers. Everything is posted online for you guys. You guys will have the